Hello, my name is Andy Schweitzer, and this is a video on limiting reactants. This limiting reactant video is limited to just particles. For example, if we have a simple chemical reaction like H2 plus O2 yields H2O, balancing wise, we would have two oxygens here, so I need to put 2 here. 2 times 2 is 4. There we go. So it's 2, 1, 2 is my rates used. These are also my stoichiometric ratios. Now, anytime we have chemical reaction going where there's 2 reactants, they're going to start being consumed at specific rates. In this case, 2 to 1. And that means if I consume 2 of these, then 1 of those. 4 of these, 2 of these. They're consumed in this ratio. So when you have 2 reactants, you then have the factor of what's called the limiting reactant. In all of our chemical reactions for this particular area, we're going to run one of our reactants down to 0. One of these 2 guys is going to hit 0. Or they both could hit 0. Something's going to run out, stopping the chemical reaction. We have initial amounts, and we have the rate used. So whenever you're calculating out your limiting reactant, there are 2 factors that will ultimately determine which reactant will run out, therefore stopping the chemical reaction, therefore limiting how much product can be made. First one is quantity. Obviously, the initial quantity that you have of the individuals will ultimately determine how long they last based on how quickly they've been used. And that's my second factor, is the rate used. So the idea of a limiting reactant is, and always will need to be addressed whenever there's multiple reactants competing against one another. If I said we have 50 of these and I don't give an amount of this reactant, I'm assuming this guy would therefore be in what's called excess. Okay? But again, that's if I don't give it. But if I were to say, I'm going to just erase that for a moment. If I say, okay, this is not in excess. In fact, I'm going to give you an amount of this guy right here. Okay? Let's say we have 50 of each. Now, before you do any math, you want to look at both of these reactants and think to yourself logically, can I figure out which one is going to be the limiting reactant? Okay? And we'll see in a moment why that's important, because all your calculations will be based off of your limiting reactant. Now, quantity and rate used. Now, if you have less of something and it's being used at a higher rate, then you can honestly say that that item will run out first. Well, think about that. Less stuff and used up greater rate. Okay, well, it easily should run out first. So in this case, we don't exactly have that. We have equal quantities, but the hydrogen is being used up twice as fast. So with equal quantities, I can say without a shadow of a doubt, this is my limiting reactant. So you want to be able to use your brain to think about which one's going to run out first, just by 2 simple concepts. And if you can't tell, then we'll move on to more of that later. But right away, I'm going to snag this is the limiting reactant. Okay. Now, once you know the limiting reactant, every calculation for the rest of that particular problem should be solely based off of the limiting reactant. Now, why is that? Well, what it means is that when I go from here to here, okay, that means that this guy is actually going to run down to 0. The limiting reactant is the one that's going to run on 0. I'm going to erase my question marks here for a second. So that means this guy is going to lose all 50 of these and run down to 0. Will I consume all of my oxygen? No. So if I were to do a calculation of from here to here, then that would be saying if I consumed all 50, and that's a 5 there, not a 0, not a decimal, 50 of my O2s, how many waters would I produce? Well, that's fine for that calculation, but are we going to use all 50 of them? No. Only the limiting reactant is the one that is going to be running down to 0, which means that's the one we're going to use all of them. Okay? And therefore, we want to base off the limiting reactant because that's a legitimate statement to say, okay, I'm going to erase this guy and say, okay, well, if I were to go from here to here, that's saying if I consume all of my hydrogen, how much water will I produce? And the answer is yes, I am going to actually consume all of my hydrogen down to 0. This guy will have some left over. So every calculation is based off the limiting reactant because that is the one that runs down to 0. And you consume all of it. All right, so I got my ice table half built. And let's do some math here. Okay, and the math is simple, but it gets more complicated, so stick with the math. Show your work. 50 hydrogens, so I'm going to go 50 hydrogens. And from 2 to 1, I'm going to get rid of the H2 and go to the O2. Now I'm solving for a reactant here. That means this is how many O2s that I need. And that's very important. At a 2 to 1 ratio, 50 divided by 2, and as you probably can see, it's 25. So I need 50 of those, but I only need 25 of these because of the 2 to 1 ratio. Now when you subtract these two values, you get 25 excess. Okay? Very often something we would like to calculate, the amount of excess. Now here, 2 to 2 ratio, I'm going to go 50 H2s at a 2 to 2 ratio is 50 H2Os plus 50. I had none to begin with, and 50 is my ending. All right. Now, pretty simple example of being able to designate your limiting reactant, determine the excess amount, and the amount of product you're going to produce. Let's try another example. All right. So let's imagine another situation. Let's go with propane. We have C3H8 plus O2 yields CO2 and H2O. My likely combustion reactions. 3 would be 3 carbons, 8 would be a 4, 4 plus another 6 is 10, so I got 5 of these guys. So 1, 5, 3, 4. So in this case, this is being used up at a faster rate. Okay. And let's say that I have 300 of these and only, let's go with 600 of these. So I have more of them. This is for my initial conditions. But this is being used up faster. And eventually you're going to be able to extrapolate in your mind and figure some things out. But in this case, it's like, okay, which one of these guys is the limiting factor? And so therefore, which one is the one I should base all my calculations off of? Again, the two factors, quantity and the rate used. Okay. If you don't know, you might think you might know. Okay. Now I'm going to think my own that the oxygen will run out first. Doesn't matter why. Twice as much, being up more than twice as fast. I think that this is going to be it. So what I'm going to do is I'm going to run this guy down to 0. Minus 600 down to 0. Okay? And then I start jumping to the other reactant. So step 1, think about this a little bit. Okay? Can you figure it out before you even do any math? If not, step 1, pick likely, okay, and then 2, solve for the other or any other reactant. Okay. Now, as I do that, again, as I show this arrow here, it's pertinent that you realize that that's the stoic ratio. That arrow means the stoic ratio, 5 to 1. So let's do some math here. Okay. Give myself a little bit of room here. And I have 600 O2s at a 5 to 1 ratio. 600 times 1, and this is going to be the O2s, and this is the C3H8. And now, again, I'm solving for a reactant. So the C3H8 is a need. How many of these guys do I need? So 600 times 1 divided by 5 equals 120. Okay, 120 propanes are needed, minus 120, and then I have an excess of, looks like about 180. All right. Now, that means for this problem, I have consumed all of my oxygen, and I still have 180 propanes left over. That means this is, in fact, the limiting reactant. I ran this one out, and I still had some of this left over. Now, if by chance, back here, if by chance you get a negative number here, that means you chose the wrong limiting reactant. Means that if I ran this one down to 0, then I would get a negative value here, which means that when I consume all of these guys, I don't have enough of these guys to keep up. So that means you chose the wrong limiting reactant. Start over and pick the other one. Now, once I know my limiting, everything is based off of my limiting. I'm going to do my math here. This question mark, this arrow here is a 5 to 3 ratio. This arrow here is a 5 to 4 ratio. Now the problem is no different than anything else. I'm going to give myself a little more room here again. 600 at a 5 to, I believe it was a 3. 5 to 3 ratio. And then 600 at a 4 ratio. The bottom one here is for the water, top one for carbon dioxide, CO2, H2O, and the math at this point is pretty simple. We'll solve for the quantity of CO2 and the quantity of H2O. So, just one example of how to determine a limiting reactant based off of the fact that you have two competing reactants. This guy would be the excess, and there, how much excess is there? 180 particles. All right, that is a very basic introduction to limiting and excess reactants.